Now I will give the floor to Bunny, and I hope that you'll give him a warm welcome of applause before he starts his talk.
Thank you. Thank you. Is the mic on? Great. I thought they were a little optimistic, thinking this would fill Sol 1 for a talk like this. But thanks everyone here for coming. In preparing for this talk, it was interesting. I realized as I was interviewing people that I lack a certain authority to speak to, for example, gender issues in computer science. And I run the risk of alienating the people I hope to empower if I get the message wrong. And I also realize it's a touchy subject for a lot of people, and I risk raising the ire of a bunch of trolls. But I think social policy should not be dictated by fear of trolls. So let's get started. So let's start talking about how much of society is included in technology. This is a study that was done on 200,000 people very recently. And the interesting part you want to look at is the purple and above bars are the people who kind of know how to use, spreadsheets and word processors and stuff. And the people, the orange and the red can barely do a search query. Like they could Google something and say, what is something? And that's about all they can get out. And so although this was done over a fairly wide age range, 16 to 65, it's easy to forget in a place like CCC that there's actually a large portion of the world that's not included in technology. And why is this inclusivity important? It becomes important when you talk about putting up to a vote. So if you want to explain situations like surveillance or net neutrality, or even like the selection of emojis to people, and you want to have a vote on it, you have to realize that that 50% line includes, it's not the majority of people who can even start to have a conversation about these sorts of things. And if you think that's like whatever, like it's just, those people are stupid, I don't have to worry about it. Sometimes the works for me attitude isn't good enough, particularly when it comes to a vote. There's a couple of very prominent examples of where we had surprising outcomes in Brexit and the American elections because of, things. And so a more specific example is like open source. I'm an open source activist, and I think that open source and the Libre movement is about empowering everyone. But if you give people source code and you don't tell them how to use it, are you really empowering them? So there's this example that happened earlier this year. Xscreensaver popped up a time bomb on my Novena saying like, this version is very old, please upgrade. So I start Googling like, what the heck is going on? Like, is this like, what's going on? And then there's this great thread where the maintainer, JWZ, sort of get some popcorn and read it. It's interesting. And he says, like, when they even bother to tell me what version they're running, I say that version is 3 years old. And then I say, but this is the latest version my distro ships. He says, then your distro sucks. And they say, but I don't know how to compile code from source, herp derp, I eat paste, and everyone goes away unhappy. So in a situation like this, it's like both the developer and the users are disempowered actually by the situation. It doesn't necessarily help to just say, like, I just put the code out there and I don't necessarily tell people how to use it and expect them to know how to use it. And so openness is powerless without inclusiveness. Sharing source code empowers 1% or even less than 1% of society. And if you think that's good enough, we need the government's help to enforce the licenses that we rely upon. And we need society's help to sponsor and patronize our efforts. And if you think that open source is a moral or social imperative, we should try to empower more people to preserve and sustain the practice. But it is not practical to teach people one by one how to code. It's not JWZ's responsibility to have told people how to compile a source one at a time. What you want to do, as an engineer, you want to optimize your efforts. You want to look for obvious issues, high leverage events that can get you a lot of gain. And so, for example, if you look around on the left-hand side is a picture from OSCON, Open Source Conference. You'll be challenged to find the 2 women in that photo. I think actually CCC is quite good on inclusivity, so the gender ratio is quite better here. But when you are looking to increase participation, it feels like this could be an area of good gains. It's like someone coming to me and saying, hey, my battery life sucks, and you find they're using a 7805 regulator to go off their power supply. Or I'm out of memory, and your memory allocator is only allocating on the odd pages or even pages. Like you've just thrown away half your resources even before you got started. And oftentimes when you fix bugs like this, the paybacks can be more than 2x. Just fixing that one problem often will help you find other problems and get even more people included into technology. How bad is the bias? Here's some recent numbers. In 2015, undergraduate degrees in the United States, only 15.7% were awarded to women. That's 2,000 women compared to 12,000 men. In that lower graph there is a comparison of computer science versus other professions like mathematics and physics. Computer science has half the number of women in it than there are in mathematics or physics even, right? So it's particularly bad in this field. And it's not just a US problem. Like here's a graph showing the breakdown in Europe, and you can see the numbers in Germany, for example, is 10.5% women getting degrees in 2000 in computer science. And then, there's some people who ask, like, maybe there's actually genetic advantage, in computing or something like this, which is a ridiculous statement. And to that, I find the only argument is just to respond with no, right? It's grumpy cat no. I actually had a series of slides where I was trying to reason through these people. I was like, you just can't reason with people who make statements that inaccurate. The fact of the matter is that just women can excel in computers and hardware. I work with many women who are very gifted in this field. Some of them you recognize, like Limor Fried on the left, who does Adafruit. There's Aya Badir, who does Little Bits. Nadia Peak, who's very influential in the Fab Lab community. There's Ji Chi on the right-hand side, who I'll talk about later on, who I'm working with on this project. Naomi Wu, who's been working on a maker in Shenzhen, who's on the confluence of design and technology and fashion. And there's another lady here, Nanwei Gong, who's also doing technology and fashion. And I'm almost sure you've seen products she's done announced on a big stage, but every single time it's always some guy taking credit for her work. And then there's Star Simpson, who is also a talented engineer, and I really enjoy her recent Circuit Classics project. And so clearly women can be involved. Maybe the bias is cultural. In my experience, China has a much better gender balance in technology fields. When I work with the factories there, I see lots of women in the offices. And I asked for a picture, actually, of a contract manufacturer I work with quite often called AQS. I said, can you send me a staff photo recently? And I just went through and counted, and it's 62% female. And this, I'm not talking about like assembly laborers. This is not like, the photos you see of like Foxconn with people in blue smocks and stuff who are just, doing rote labor. These are people who are doing staff. They're skilled in component selection, sourcing, manufacturing, project management, logistics, and design, and so forth. So perhaps, if you can see evidence that it's possible and other cultures are more inclusive, maybe there is a cultural issue. And there are a couple experiments in cultural change that offer two of them I looked up that were well-documented studies involving cultural change that indicate that culture is a significant factor affecting inclusivity. So for example, Carnegie Mellon did an experiment where they tried to change the culture around their curriculum, and they managed to go from less than 10% enrollment to over 40% enrollment in 5 years. Of females. And in Harvey Mudd, they had a similar result from 12% to 45% in 5 years. And I kind of read through some of these, and the key insight I got is that computer science is unique in assuming that you already know it before you study it. It's kind of like a medical program expecting that you've already done surgery before you enroll, or a law school expecting you've already been to trial. But a lot of computer science programs already assume you can write reasonably complex programs in C-like language before you even get to college. And so the intro classes are literally called weeder classes. They're there to get rid of people who weren't exposed to computers before they got to college. It's like walking into a Chinese class that's introductory and seeing a bunch of Chinese people there, and then you have to get the best grade in that class for you to get on. And you don't even want to participate in that situation. And it turns out that this bias starts at a young age. On the right-hand side, there's a ratio of the number of children who are being given engineering construction kits by gender, as analyzed by name. This is a recent study that was done. And because the bias starts at a young age, by the time you get to college, if you're like, hey, I want to go to computer science, you just don't have the chance to really catch up at that point in time. You're excluded from the experience. Now, Harvey Mudd and CMU were able to address the issues by redesigning their intro computer science courses, by offering courses that assume that you know nothing in the beginning and to help you catch up. But we can't count on changing every undergraduate computer science program, so we have to start earlier. We need to find a way to change the culture. And so I was thinking about this a little bit more, and I happened to be reading a biology textbook, and I came across an interesting thing about sauerkraut. I love sauerkraut. And it's made with nothing more than cabbage, salt, and water. And every time you put those three ingredients together, you always get sauerkraut. You don't get something else, right? You don't have to start the culture with anything. It just naturally turns into sauerkraut every single time. And I read a little more about it, and it turns out that at the beginning, when you have cabbage, you have a neutral pH, and you have all kinds of different bacteria and yeast on there. And there's one particular species of bacteria that eats the cabbage and releases lactic acid. It makes it more and more sour, creates more and more acid, eventually killing off everything around it until there's only one species left. And every single time you put this recipe together, you always end up with sauerkraut. So if you want something other than sauerkraut, you can't fix the problem by just adding more cabbage, right? You have to do something to change the culture or the conditions to get a change in the outcome. And this sort of caustic environment actually affects both genders. I have a good friend and my collaborator, Sean Cross. He's the developer for Novena, Firmvale, NETV, Chumby, and Linux. Like, he's the reason that the stuff I build isn't just shiny doorstops that do nothing. Like, the software on it actually is very important. And he's a brilliant developer. He's supportive and modest, and he really values a work-life balance. But this is not kind of a personality type that sort of thrives in a caustic environment. Neither him or I are really lean-in types. Some of you will recognize that word. He got his undergraduate degree in psychology for various reasons, and as a result, his opportunities were limited. Initially, he was forced into like QA and support roles. They wouldn't want to give him a development role until I saw some demos he did that were absolutely amazing. I was like, I said, I want that guy in particular working on my stuff, and then we were able to start doing our adventures together. But that sort of environment that he was originally put into didn't allow him to really stretch his legs and become everything he could become. So to change the culture, you have to change the ingredients. I like sauerkraut, but I also like beer. And if you didn't add hops to your beer, you would end up with kind of sour tasting beer half the time. And that's not necessarily something that's desirable. And so I've been doing an experiment in change in paper electronics. And the question, I guess, is that by changing the ingredients of electronics, can it change the culture around it? So instead of going with wires and breadboards and so forth, what happens if you start with like paper and copper tape and so forth? And this is an idea that was thought of by G-Chi, and we ended up starting a company together. We actually have a company called Chibitronics around this, and it's interesting to note that the company itself is actually primarily female. I think the last thing you want in something looking to create change is a group of men making recommendations about what we should do for diversity. And so if you look, the initial results of our experiment has been positive so far. This is from G's doctoral thesis, where she went and analyzed the sales numbers of Chibitronics from the beginning to today. In the beginning, we were 70% male. The green section is male and the red section is female. And the blue is, we couldn't tell from the gender from the name. And then over time, we organically grew into a more stronger female audience. Right now, we're doing about 70% female, which is pretty interesting for an engineering construction kit. And something that I've been trying to figure out is how do we go beyond just simple circuits and into something where people can learn or even love to code? And so we've come up with a learning system that's aimed at increasing diversity, particularly in computer science at young ages. And so analyzing our experience in sort of Chibitronics so far and try to think about what were the things that were important factors in having it become more inclusive. I find that balance was very important, so we want to treat engineering as equal to design. Familiarity is very important, having materials that are universal that people feel familiar getting into, and also simplicity is also very important. So I'm going to go through each of these three principles in a little more detail. So balance, engineering is equal to design. So there are many good examples that we're all familiar with of how design can revolutionize technology. The MP3 player was sort of a boxy, uninteresting thing until the iPod came out, and then the iPhone clearly revolutionized smartphones. And there's a thing where blueprints alone are kind of inscrutable. If you just look at the thing on the left, the thing on the right, you don't really know what it's for. It doesn't have a meaning to it in and of itself. But this is the code in the prototype circuit for something that was much more immediately relatable. This is the dandelion painting that G did, where she took electronic circuits and put them on a backdrop, and then overlaid on top of it a picture of dandelions, and you can actually walk up to a blow on it, and the white dandelions would like let go of their fluff and drift across the page. It's a magical experience overall. And so she's able to go ahead and take what is inscrutable and turn it into something that's immediately relatable by combining engineering and design. And so the curriculum that we've created treats engineering design as equal partners. You start with an exercise, for example, here to create a pressure sensor. And then you flip over the page and then you're challenged immediately to tell a story. Why did you build this pressure sensor? You can see the hint of it here. There's a little heart, and as you press it, the red light starts to glow. And then you're challenged to go ahead and draw a story over the blank sheet. And diverse thinking is more inclusive, I think. So when you measure achievement only on one axis, there's only one direction where you can sort of get to, and it's a sort of a thinning out of the ranks as you get towards the ends of the axes. But if you go ahead and you say, let's look at both engineering and artistic ability and try to combine them together, you have a much larger space where you can create interesting things. And it's important not to just write it off as like I say, okay, well, we're going to put boys on one axis and girls on the other axis. Like in both axes, you can have people who achieve very well in either one. But when you go ahead and you look at it in a multidimensional space, we have orthogonal parameters, you create a bigger space for achievement. And I think that can help get more people involved in technology. Familiarity is the second principle, and using materials that are universal. So familiar things are naturally comfortable. So a lot of us started electronics looking at breadboards on the left-hand side. And there's a little magic that happens inside them. That you have to sort of take them apart and show the people the underside that shows the wires connect underneath for you to get them. It's not something that a lot of people are familiar with initially. Whereas Papercraft, and in the style that we use it uses materials like tape and paper. You lay down the copper tape, and that's where the electrons go. It's very clear. It's very familiar. Paper is universally familiar. It's an everyday material. It's books. We print on it. We use it for bags. We make origami out of it. Paper is also an incredibly expressive material. So you can do a lot of very interesting things from the artistic side with paper. This is a sample of artwork that was created as part of an exhibition that my collaborator Ji Chi did. You can go to papercuriosities.media.mit.edu to check out more of them. But there's a lot of really fantastic things that people were able to do with paper and just light. And we want to extend that to even more with programming. But not only is paper an expressive material, it's also an engineering material. This is a picture of actually a quick prototype that Zobs came up with of a bias network for a split core transformer. Just need to come up with like a circuit board, like instead of taping a whole circuit board, let's go ahead and just use paper or copper tape and make it all happen. And it's really interesting that you can see it's self-documenting, right? You don't have to guess what the values were, where things went. You can write on the paper and it just all comes together. It's working with axial and through-hole components. And so paper versus breadboard is an interesting sort of comparison. I have the two side by side here. Paper is compatible with both surface mount and through-hole types, whereas breadboards can only do through-hole. Paper natively supports comments, whereas breadboards, you can't really write on them. Paper, it's thin and flat, and you can fold it into 3D shapes. So when you're done, if you want to go and fold it over, you can just go ahead and do that. You can't do that with a breadboard. The substrate cost is practically free. Breadboards are relatively expensive. But on the downside, the substrates are not reusable. You may require some soldering, and the components are typically not reusable, which has been a barrier for us to try and get into more expensive stuff like microcontrollers. And so G came up with this idea of putting a microcontroller on essentially a paper clip, a notebook clip. This is a picture from our thesis on the top, and we've been refining it into the thing that you see below, which is a rigid flex circuit board, which has a rigid portion of the PCB and a flexible portion of the PCB. And we can use it to wrap around the edge of a clipboard. So you can go ahead and wrap it around the edge of a clip. You can craft circuits on pieces of paper. You can let it down, and then the circuits themselves are in contact with the microcontroller. And so this is a very familiar format. You don't have to explain to people a lot about how to get started with this, what to do about it. You just show someone how to use it, and it's very natural and it's very easy to use. So we're working now on a sort of a general notebook clip type prototype where you just go ahead and you put your your microcontroller on a clip. You go ahead and clip on the edge of a piece of paper or notebook, and you're off encoding. But the final thing that's very important is simplicity. How do you actually get code onto the device in the first place? Great, you have a piece of code, but then what? Like, this is like step 2, step 3 profit, right? Like, what's the step 2? It's hard to get code into a microcontroller, right? It's like you have to have a cross compiler, and then you have to have some drivers and blah, 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 all this sort of stuff. And the thing is, configuration isn't science or logic, right? It's convention. Like, you may be awesome at like command line stuff in one distro of Ubuntu or whatever Linux, and then you go someone puts you in another machine, like a Windows machine, like where the hell do I like configure USB drivers at, whatever it is. It doesn't require someone to necessarily be intelligent to understand how to configure. It's just you have to know the conventions. And the problem is that when people ask stupid questions, they're like, just read the fucking manual, right? There's this very sort of caustic environment starts coming back at them. Why are you asking me these stupid questions? You should know these things already. And so we really want to avoid pushing people into that sort of cult of RTFM in the beginning. Otherwise, you just start creating more of that sauerkraut culture again at the end of the day. And so a challenge we were faced was finding an interface that's truly universal to program a microcontroller. There's things like USB and Lightning, but all of them require drivers and so forth. But then there are things like eyes and ears. These are how we interface with our computers, the analog whole, so to speak, right? Ears are pretty universal, eyes are pretty universal. So I looked at those interfaces as options, and sound is, simple, it's ubiquitous, has good browser support. Headphones are on everything, almost everything. I don't, want to have to use your proprietary fucking ugly microwave transmitters in my ear to listen to sound. But more importantly, sound is also data capable. So if you use sound, we find we have an ability to use the cloud and sound to upload compiled code. And so I'll talk a little bit more about how we make that happen. This is where the talk starts to get a bit more geekier. It turns out that making things simple is really, really hard. We've been trying actually for over 3 years to kind of make a version of this product. The first 2 generations were completely stymied by configuration problems. We tried doing generation 1, generation 2, where you can see on the bottom here are @tiny based microcontrollers, which were really difficult for people to use. Gen 3 was sort of like the prototype that G came up with, and Gen 4 is where we're kind of finally getting to something that we might be able to share. And we designed it from the bottom up for simplicity. So I'll go through the infrastructure, like how do we get code, turn it into sound, and get into the microcontroller. So we'll start with what I call the phi layer, kind of loosely a phi layer. We use AFSK modulation, audio frequency shift keying. We use 2 tones to represent a binary 0, 1. It's exactly like those old modems from the 70s, the 80s. I don't know if any of you are old enough to remember it. But we use 8.6 kilohertz and 12.5 kilohertz roughly. And we picked the tones to be MP3 survivable. We wanted these songs to be able to be encoded into MP3s and played back, so you could share songs and not just source code if you wanted to later on. There was a bit of a challenge implementing this because we wanted to pick an MCU that had a price of under $1, because that rigid flex circuit board you saw where we had part of it rigid, part of it flexible is not cheap. That actually runs up the cost quite a bit. So we had to find other ways to keep the BOM cost reasonable. And we also, in addition to be under $1, had to be able to do about 20 megamax per second of performance, had to have integrated ADC, open source friendly was very important to us. And we also wanted to be backward compatible with a lot of the community stuff in Arduino. Here's a kind of a big chart of some microcontrollers that were considered, from the @mega to the @tiny, general plus, and blah 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 and so forth. There are definitely some cheap microcontrollers you can get out of China, but they're not very open source friendly, so we kind of threw those out. There's some very popular ones like the Atmega, but they don't have the performance, and they're also way too expensive. And then you get down to some of the other ones like the PSOC 4, the XMC 1000, the LPC series. And basically we found is anything under $1 in that range didn't have the performance that we needed, which left us with basically one of two options, either STM32, the F0 L0 series, or the Kinetis KL02. We settled on a Kinetis. That's currently one of my favorite series. Probably mostly just personal bias, I guess. It's a 48 megahertz Cortex M0 Plus, which means it does a 32-bit single cycle multiply, very important for the DSP. Has 32K of flash, 12-bit SAR DAC. In volume, it's about 90 cents to 97 cents, which is good. There's no NDA requirement for the documentation. And unlike the STM32, it has fast GPIO bit bang capability. One of the weird things we found about the STM32 is that when you want to bit bang, there's this, I guess, a feature where they try to do synchronization of writes through some sort of gateway into the GPIO, but it would means that your maximum bit bang rate was limited. It would cause trouble for things like driving WS2012 LEDs or doing USB low speed. This is the data sheet for it. You can go online and read it and look it up all you want. When it comes to connecting audio, there are three issues that we had to solve. You can't just put it directly into the microcontroller. We had to fix the DC offset. We had to think about the connector cost and height and the cabling issue. DC offset is important because audio itself isn't necessarily, it's basically an AC coupled signal, which means half of the waveform is going to be below ground. If you feed that into the microcontroller directly, you only get half your waveform. So we have to recenter the audio. Second is the connector cost and height. Audio connectors aren't free. They're also thick. So they're 5 millimeters tall. The tallest component on our board otherwise is 1.7 millimeters. If you want to be Papercraft friendly, we really want to make it thin so you can fold paper over it without having a big lump in the way. And also cabling, quality cables are expensive, and cables are also easy to use, especially in the classroom. If I have to have the teacher with multiple cables to plug in their computers, they're going to lose some, and it's going to be a frustrating experience for the teachers. So we came up with this kind of hybrid solution where we designed a cable that uses the 5th pin on USB OTG. If you look at USB, it's commonly known as a 4-pin standard, but the OTG connector has this 5th pin, which identifies whether you're a host or a device. We just sort of say we don't need that. We're always going to be a device. We don't have to have the AV capability, and we just wire the left audio feed into that pin into our device, and then we created a Hydra, a Y-shaped cable. That gets us roughly 2 cables for the cost of 1.5. So it helps us save costs. It solves the thickness issue. And the solution ends up looking a little bit something like this, where you have one thing plugging into the USB micro connector, and then you have a head of both an audio connector and a USB connector for power. The electronics solution, we AC couple with an R2R network or an RR network to center up the audio. The 1 volt peak to peak of audio centers up nicely in the 3.3 volt range of the ADC. FSK waveforms are pure sinusoids, so we don't have to worry about DC balancing. That's cheap, a couple cents. It turns out that there's this bootstrapping problem. If you ever touch like a MacBook or something and you feel that sort of like buzzing sensation off of it, that's because that case is like floating up to like 50 volts or something like that, right? And so when you go ahead and you plug a headphone jack in, there's this awful pop that comes out, and that pop is actually enough to go ahead and put the microcontroller that we have into latch up. And so we have to put these like diodes to absorb all of that voltage difference and when you first plug it in. And that's actually the most expensive part of the design. It's 7 cents. And then we wired up the USB D plus D minus lines to the MCU. Why not? And it turns out, well, if you went to Sean's excellent talk yesterday, he implemented a low speed USB stack that allows us to essentially turn LTC into something like a makey if you want at the end of the day. Or you can just use a non-compliant bug port. You get your RX and TX out of the thing. So on the software side, we just do non-coherent FSK demodulation. It means we convolve the incoming samples by the sine cosine of each frequency. So we have to do 4 convolutions. Each convolution is a series of multiply accumulates. That's 250 multiply accumulates per sample. At our sampling rate, that's 20 million multiply accumulations per second, hence the performance requirement of the MCU. We sort of started from LIN modem and sort of refined it until we have what we have now. You can see the two repo links for it. At the 03 GCC setting, it uses about 65% of the CPU. So there's not a lot of CPU left over for doing anything else. If we miss a packet, there's not enough RAM for me to buffer anything. This all has to happen online. So if we have to do CRC or hash checking or forward error correction, it all has to happen in parallel with the demodulation of the audio. And so this gets me into what I call the MAC layer. It's not really a MAC layer, but this is sort of like how we deal with sort of errors and so forth. The audio starts with a herald, a control packet. If you actually listen to the stream, you'll hear a little burst of static and then about a 1 second pause and then the other stuff coming through. The reason why the herald packet comes first is that you want enough time for the microcontroller to erase its flash block if it's going to be reprogrammed. Otherwise, you're sending data while it's erasing flash, and that takes a long time. Every single packet is protected with a Murmur 3 hash. We picked that because it's 32-bit hash and it's fast and small. And we have to compute this in line with FSK. We couldn't do anything like MD5 or anything more computationally expensive because we just couldn't fit it into the inner loop. We also had to do some baud striping. So in order to recover the baud rate, you have to have enough transitions. So we do a simple thing where we XOR every 7th byte with 5.5 and every 15th byte with AA, and we get enough transitions with typical computer code. I mean, of course, you can create something pathological that doesn't work for this, but usually compiled code doesn't have a pattern that matches up exactly to that. And then the data packets themselves has sync header version, some sequence number, and the whole thing is again protecting the hash. And then our FEC, our forward error correction, is we transmit the data 3 times. So pure redundancy. It's not really like a ECC or anything like that. And the reason why we had to do this is there's no back channel. Like microphone pinouts aren't standard. If you ever try to take an Android headset, plug it into an iPhone or vice versa, you know the frustration. And we want to avoid people having unexpected bad surprises. So we had to build a protocol that was feed forward only. Errors do happen in transmission. So for example, if you're programming from a smartphone and someone sends you a notification in the middle of it, it'll go bing, and that will cause an error, which will make your packet go away. And so we have to do a retransmission. And we find that 3 times is enough to basically get through almost every condition. And also because 60% of the CPU and almost all the RAM is used for demodulation, there's no CPU or RAM left for any error correction code like Hamming or SecDet. We just rely on redundancy and pray. So a little more about the next layer up. Once you get the code in, what happens next? We have an audio updater bootloader. If the code's good, we jump into ChibiOS, which is a full multi-threaded microkernel OS, and it has a bunch of application threads beneath it. Out of the 32K in Flash, we use 22K for the bootloader syscalls and the OS, a bit for some signature and interrupt table management, and it leaves 9.5K for user application code. Now, ChibiOS, even though it has the name Chibi, it has nothing to do with Chibitronics. I want to be very clear on that. It's made by this guy, Giovanni Di Sirio. It's very actively developed and maintained. I'm particularly fond of the OS. And the Chibi is just a borrowed word from Japanese, which means cute or tiny or small. So it's appropriate in both cases. The ChibiOS itself has a HAL abstraction, preemptive multi-threading, semaphores, queues, synchronous, asynchronous I/O, thread-safe memory pools and allocators. So it's a very, it's a feature-rich OS that fits in a few kilobytes. Zob's added to it a syscall extension, which allows us to essentially do dynamic linking. It uses the ARM SVC call mechanism to create 256 thunks. That allow us to share OS-based code with the application code, so we can implement the Arduino emulation layer, EEPROM hybrid emulation, all that sort of stuff. And the reason why we did that is we had to fit within the patience of a child constraint. So 8,000 bits per second means about 1 second per kilobyte of code uploaded, and a child will lose interest in about 5 seconds. Okay, now the children aren't listening anymore. Basically, the baseline Arduino 0-LUT binary was about 8 kilobytes when we first started looking at it. And that would have been about 8 seconds to get the baseline in. So we wanted the average binary size to be less than a kilobyte. So we did this syscall extension to try and preload most of the bloated, commonly used libraries on Arduino land, like floating point operators and string operations, and also try to streamline the general loading process as a whole. So typically, the average getting, kind of hello world getting started binary is just a few hundred bytes. And even the bigger programs are only a few kilobytes. And so when you want to compare the available code space on, say, an Arduino Uno versus LTC, consider that we've already preloaded about 12 kilobytes of libraries. And significantly, I wanted to make a product that was not just for kids. So the LTC itself extends from novice to startup. We want to create an on-ramp that can eventually lead to professional level development, right? I didn't want to create something where if you got into it and you just sort of ran off a cliff and you couldn't go any further. So, for example, the threading APIs are exposed in assist calls. We want to make DirectOS, a bootloader development possible via OpenOCD. If you saw Zob's talk yesterday, you would know how to do that. We made sure that the hardware components were China ready, but also compatible with small-scale prototyping. So if you were to get into this and say, hey, I've built something and I want to make a few more of them, you have the option of both going to DigiKey, and if you want to build even a few more of those, you have the option of going to China, and both of them are very low friction in that case. And of course, everything is all open source. You can go to GitHub and either to mine in his repo, you can find all of the stuff there. That little section down there is just a display of the multi-threading interface inside ChibiOS. And so finally, talking a little bit about the experience layer, the user experience. It's important that we had a very sort of simple user experience at the end of the day that just always worked. So it's a web-based interface where you can go ahead and code, and you can pull up some examples, and then just hit upload, and it starts playing out your compiled code as sound. There's a little bit of stuff behind it that had to be implemented to make that happen. So we have a web IDE and examples that uses CodeMirror as its base. And you can store your sketches locally using web storage. But if you want to go ahead and share your code, we would like to point people towards GitHub, because that's where we should point people, I think. The final C files that you want to upload are then sent to a server. It's a Docker image that's Kubernetes ready. Turns into a binary, which is sent back to the browser, and then there's an audio modulator that attempts to modulate it using web audio or wave via JavaScript. And if an error happens, we actually have an MP3 fallback mechanism where we would then modulate on the server side an MP3, send it over, and then have them do an MP3 player embed. The compilation server requirements was that we want to have like very minimal bandwidth requirements. So we want to be able to run the server like forever and not have to be burdened by its cost. And so the average sketch is about 1 kilobyte, and the average binary is about 1 kilobyte. When you want to buy this thing, visiting our store pushes over a megabyte of content. So we figure that was fine, right? If we were willing to serve you the images to buy this thing, we can certainly serve you the bandwidth to compile for it for quite a long time. The overall design itself is stateless, so it's legally difficult to obtain consent from people who are under 13 years old to store their data. And so it's a very important feature to us that we have no user accounts. We don't want your stinking data. And if you want to go ahead and share code with people, you go to GitHub and you share it via there. That's a planned feature, but we should have that in. This greatly simplifies scalability and maintenance. So as we need to go ahead and scale up, we just spin up more instances. If one of them falls over, we don't care. There's no databases to restore. There's no concerns about losing user data and whatnot. And so you can go ahead. We have some Docker images. If you want to spin them up and run them yourself and reduce our load, you can do that as well. So audio modulation, we needed a just works method that doesn't involve uploading 100 kilobyte audio files. Web audio would have been ideal, except that as of like late 2013, it wasn't supported in OS X. And if you look at sort of the school environment or kids, a lot of times kids are getting hand-me-down phones from parents. And so 2013 is kind of the range you start bumping into. When we did early tests and field trials, we're finding kids are like, oh, my browser's too old. I can't modulate. So you go into Wave, which can be generated browser-side by JavaScript, and now you have 89% of the browser supporting this. And you have to go all the way back to 2009 to really old versions of Safari before you lose support for that. That seems all good, except there's like this red column on the left, which is Internet Explorer. And you're like, oh, why do we care about Internet Explorer? Turns out that 27% of desktop installs are Internet Explorer. That's as of August 2016 Wikipedia, if you can believe it. But what we're finding in particular is that it's significantly highly used in schools and institutions with inflexible IT policies. They get Windows, they install it, and they don't want you to install anything on these things. And so you're stuck with Internet Explorer in a lot of school environments. And so in order to handle that situation, we would fall back to the server-side codec, send an MP3 file, which as of IE9, you can go ahead and play that. So hopefully this gets us pretty good coverage. It's about 93% of the browsers out there. So the net result at the end of the day, of all of this is that we have broad compatibility and simplicity and ease of use. We have a device that can be programmed with everything from a smartphone to a laptop to even if you had a high enough fidelity record player or a cassette tape, you could go ahead and pre-record your songs onto those. And part of the idea of this is that we wanted to try and draw on people who would even be afraid to code in the first place, but had some desire to customize their technology. So if you're a crafter and you want to create a certain pattern of lights and you don't think coding is for you, we wanted those people to be like, help, I want to have something that does this sort of thing. And someone could share you their song and they could then program it and be like, oh, hey, look, I can modify my technology. This is something I can do. But then hopefully they would be like, I want to do a little more. I want to do a little more. And then they're just like, well, maybe I should just look at the code. And they find it just a bunch of numbers they change. Like all of a sudden, they're sort of tricked into getting into the whole coding exercise by sort of being pulled into the idea that technology is something they can control and not something that they're sort of beholden to at the end of the day. So LTC fosters diversity through a combination of balance, familiarity, and simplicity. We look at making sure that the curriculum itself balances, design and engineering. And we try to use familiar interfaces, materials, such as paper and copper tape and so forth, to try and bring more people in. And we shoot for a very, very simple experience getting started through the web-based interface with the audio upload. So at the end of the day, open source is built on inclusiveness. It's not just about sort of committing and forgetting. It's all about pulling and merging and forking. You don't have to always take the pull request, but it's really important to accept new ideas and to improve the code base. And so if we care about, open source, we need to empower more of society to understand its value, or society may end up determining its value for us in a vote. And if they don't understand what they're voting on, it doesn't necessarily go in the most enlightened fashion. And so that's my talk about the Love to Code platform. We'll have a beta in 2017. You can follow Chibitronics or visit chibitronics.com for more updates. If you go to the fail overflow assembly, this is a picture of the sign there. The little lights on the bottom of the fail overflow light are being driven by an LTC microcontroller right now. So you can walk over there with your whatever device you want and go to ltc.zobs.io, which is the current staging server for the latest stuff. Plug in the headphones, write some code, press and hold reset on the microcontroller, and hit upload and see what happens. I think we are looking for more evidence to see if our stuff works truly cross-platform. So if you come by and it doesn't work for you for some reason, we'd like to know what actually has gone wrong. And that's it. Thank you.
Thank you very much, Bunny. And now for questions. Do we have any questions from the internet? And while we're getting the questions from the internet and the mic working for the Signal Angel, you can stand up towards the microphones if you have any questions in here. And while we wait, we can have another round of applause for Bunny. Could we have a question from microphone number 1, please?
Hi, Bunny. First of all, thanks for the talk. I've noticed that for the development environment, you are using Arduino flavored C++. Are you sure that's a good thing for beginners?
Yeah, that is actually an interesting debate. So there are block-based programming languages like Scratch that are very good for beginners, and we have active efforts to also develop that as well. It's kind of my feeling that I wanted, though, to create an on-ramp to get people like, I'm targeting sort of like people who want to go undergraduate level college courses. And so if you enter in one of those situations and you've only been doing like block-based programming and you haven't seen the syntax and dealt with semicolons and stuff, then it can be a little overwhelming. And so I also don't necessarily think that C++ or the Arduino libraries are necessarily the best introduction, but it's very well community supported at this point in time. I think there's like sort of like a daydream that maybe we would do, like we're talking today, like a Rust-based system that could let you compile and upload code to it or something that is kind of neat and cool. But the problem is so few people use these languages that if people had questions, like we wouldn't have anyone to answer them. So.
I see. Thanks.
Yep.
I have a question from the internet.
Hello, there's a question from IRC and it's a bit long. How can we tackle stereotypes when the image of the sweaty male teen in a darkened bedroom hacking the planet is the mainstream? I see this as a lack of understanding of a whole number of factors, notably a lack of understanding of the capabilities of computers and how to use them, the wider lack of diversity in the sciences, as well as cultural ideas of what an office run by male management is like. How do you think that we can tackle this stereotype in culture?
All right. I think that was a lot of words, which I think I'm trying to even parse in my head. I think I had a buffer overflow about halfway through that. I think so. I caught part of it. It sounded like there's an issue with the stereotype that exists in society. But then the question was, how do we tackle that stereotype? I guess. I mean, I guess the guy's not here, so he can't.
Yes, that was the question.
Yeah. Okay. I mean, I think by just in general, like what we're proposing here is like it starts from the beginning, just becoming more inclusive at a base level and changing the culture and getting more people involved. That stereotype will naturally sort of melt away as it becomes more inclusive and more people like become involved. I think. I don't think it's something that. Yeah, it's not something that you. How do you say? You can't. I don't. I'm having struggle to find the words for what I'm trying to say here. But I think that basically at the end of the day, the theory that I have is that if we aim to be more open-minded as a community, and if we aim to be more inclusive, particularly at the beginning, the culture should naturally grow into something that has, I think, less of that stereotype around it. People become more aware. As more people can become aware of how we are and how we operate, they will say, hey, that's not the stereotype anymore. These people aren't all like that at the end of the day, I think. So
I have a question from microphone number 4.
Hi. Yeah, so my question is a little bit related to the last one. When I was younger, I was very curious. I actually wanted to learn program and more technical stuff, but I just couldn't. I didn't know how to get the information. Our school didn't really have a program. Mm-hmm. So with your product, you're offering a great opportunity to learn, but the problem is to get it to the people who want to get involved. So do you happen to have a program? Are you involved with schools or people?
Yeah, so that's a good point. Availability and getting these things into the hands of people who want to do it is very important. And so absolutely, yes. I mean, one of the core focuses of Chibitronics is schools. We do a lot of outreach and we try to engage with them directly. It's kind of, my marketing manager's going to kill me, but it's like a secret that any school asks to get 20% off, right? Just for asking, saying you're a school, right? And then, and so on and so forth. So but the thing is like we want to, give discounts and get it into schools because that's where it makes the most difference at the end of the day. Another thing is like when we were trying to put together the supply chain and, there's a lot of effort we went to actually getting the stuff to fit in this really low power, low cost microcontroller at the end of the day. And a lot of that boils down to like the cheaper we can make it, the more accessible the technology becomes. And so we wanted to be able to create something that comes at a price point that schools could afford and get into a situation. Now, that there unfortunately like schools that are so poor they literally can't buy dirt. Like we were contacted by a school in Pasadena who was interested in it, and they're like, to give you an idea of a situation, we had to cancel the gardening program because we couldn't buy dirt for the gardening program. I'm like, okay, like I really want to help you, but there's some other major socioeconomic issues happening when your school is underfunded to that point, and we have to address those problems maybe separately. But ideally, we can get this into as many hands as possible by focusing on the schools.
Brilliant. We have at least 3 more questions, so please remember questions and not comments. Microphone number 3, please.
Yeah, first of all, great work. I really like the idea of uploading code using audio, so I have a question to the technical aspect of this. So why didn't you put a microphone on the PCB so you don't need the wire?
Yeah. That's a good question. We had thought about that, and I thought that would have been really cute, except that when you consider that you have a classroom full of students and they're all trying to program, and then you have students programming other people's stuff, it ends up, A, it's noisy, and B, there's a lot of crosstalk. It's certainly possible to do it microphone-based, but we decided that it would be more, you get less crosstalk if you use it headphones directly.
Yeah, good point, thanks.
Yep.
Microphone number 5. Questions gone. Microphone number 1 then.
Yeah, my question is, did you look for, there are ICs who emulate AFSK directly, so you don't need the processing power on the microcontroller itself. So did you look for those ICs?
Oh, a separate IC that could do the AFSK modulation directly, so I didn't have to do it on...
Yeah, you have a wider range for microcontrollers to choose.
Right. So some sort of hardware-assisted situation for doing this. I mean, it turns out that when we're in this sub $1 constraint, like even adding an op-amp on the outside, for example, I talked about the DC level adjustment. Like we thought about using an op-amp initially, that would have added like 10 cents. That would be 10% of the microcontroller's cost. And so we're getting down to optimizing pennies, adding a whole another packaged integrated circuit outside to handle the AFSK as like a DSP or a prepackaged solution. It would have to be like under 10 cents for it to be worth it. And that type of technology isn't really available today in that low cost because, partially because no one does AFSK anymore. Like the modem chipsets are all dead and buried in 1 micron CMOS anyways. So yeah, it would have been great if we could find something that could offload that from the CPU, but we couldn't find anything like that.
Thanks.
We have 1 more question from the internet, and then we might try and squeeze 2 more questions in.
Okay, a question from Twitter. Do you know about the Calliope Mini and the Microbit Edu, and are these comparable to your attempt?
The Calliope Mini and the Microbit, sorry, what? Microbit audio, you said?
That was not included in the question.
Okay.
Let's try and see if you can get that answered through Twitter.
I do know about the Microbit, and that one's a very interesting one. I was trying to hear the Microbit audio. Was like, oh, are they doing audio programming too, or not? But I think the Microbit is more a conventionally programmed microcontroller. I haven't heard about the other one. But as far as I know, I think we're the only one that does AFSK-based programming, audio-based programming, which allows you to sort of open up to a much broader range of devices. And part of the reason it turns out that it was so important for us to get into audio programming is that a weird thing is happening in the world in that kids don't have notebooks today. They don't get laptops. The first computer a kid gets is a tablet or a smartphone. And so when particularly at a younger age, if they're introduced to coding and they're giving a homework exercise and they come home and say, Mom, Dad, I have to use your work computer to do my, homework. They say sorry, use your smartphone, right? And so we really wanted to create something that would enable, kids who are, the dominant thing they're getting, say, are smartphones and tablets to be able to try to learn coding. It's admittedly very difficult to code on a touchscreen because touchscreen keyboards are crap for that. But I'm really hoping I think that's a problem that's solvable if someone actually cared to write a better keyboard interface for coding. It's like right now they're all just optimized for texting.
Microphone number 2.
I'm kind of surprised the taping down copper and soldering on paper works as well as you like, did you have problems that you had to solve to get that to work? And is soldering, is there not a better option than soldering for that?
So yeah, maybe I didn't make this very clear, but so copper tape and paper works great. First of all, I mean, copper tape itself has a nice property. It's very easy to cut into finer pieces. So if you need to go finer pitch, you just slice off a piece, and you can do like SO16s and SO8s and stuff. The soldering is only necessary if you don't have a solderless method. So the typical way we do teach with, for example, the LEDs is you have stickers. We actually use a conductive adhesive on the back of flexible circuit boards, so that when you craft your first circuit, you just lay down copper tape, you put a sticker down, and you fold over the corner, put the battery in, and it lights up. So there's no soldering involved. That's actually one of the constraints of our technology, is to get the dangerous soldering irons. You know, apparently soldering is forbidden in the hack center. We were told that earlier, like it's a dangerous activity, and so we had to get that out of the classroom. So yes, actually, once you get into the, once you have the conductive adhesives, it's pretty easy to use. And surprisingly, like paper itself doesn't burn at all when you solder it. That's something that originally, when G showed me the technique, I was like, can you really do that? Is it going to catch fire? No, it works pretty well. The copper tape itself is a really good heat sink, so it pulls out almost all the heat away from the paper. I mean, if you just stick the solder tip on the paper, you'll burn a hole through it. But if you're soldering the copper tape itself, so much heat gets wicked away that it doesn't end up affecting the paper.
Good, excellent. I think we don't have any more questions. Could you please give Bunny a warm round of applause?
Thank you.